Okay, so data manipulation, there are two types. We're going to do manipulation on Word data or file data. Right here, if I was to go online, let's see, here's the last one that was open. Let's let the go online button. Right here, these are our data files. If I was to open up one of these integer files, I could do, hold on, I'm going to have to make some more. So we're going to have to make some more data files because it's hard to explain with just one. Like 10. So integer files here, we can do manipulation just on one word, or we can manipulate the whole chunk of it, right? We can get that bigger. We can do manipulation on this, or we can do manipulation on the whole mess. Are you with me? All right. So here's our file or table. That's just what I showed you. They have some manipulation instructions. They are located up in the instruction toolbar. Move, logical, file, miscellaneous. Half of these you'll probably never use. But we'll talk about them because you might run across them. We're trying to do troubleshooting like what is this doing? All right? So, easiest thing to do is a move statement. We're going to transfer data from one place to the other. All right? We use the move statement. Let's show you how that works. We're going to come in here and do a little program edit. I'm going to find a switch somewhere over here. We don't care what. We're going to drag it off. Put it on there. I'm going to come over here to our instruction toolbar. Click on the move. Insert a move instruction. We're going to come over here to our source. A little hard to get in here. Sometimes you have to copy and paste them out, or you could just type it. Pull this over a little bit. All right. So
why don't you ever just move it over one spot like that? You got one.
well, if you've got some temporary data, maybe you're pulling a part speed or some value that's rapidly changing, you could have a freeze button so the operator can actually see what's going on. That's possible. It gets abused. Maybe somebody comes along in a few years and does some changes and they go, I don't know what they're doing over here, but I know I need that data, so I'm just going to grab that data and move over here and work on it. Because I don't understand what they're doing over there, and now you've got the same data in two spots. That makes sense? Yeah. Another thing is maybe a recipe. You have a recipe storage location for a palletizer or some process, and you go grab it out and move it into the current recipe. So let's put a value of 5 in there. Notice we're moving from N7:0 to N7:1 off the switch. I'm going to flip it. And now I'll move a 5 over there. Every scan it's moving the same amount of data. I can't change it. If I was to go here and try to put in if I was to go to the destination and try to change it, it won't take it. It's always moving. So that's a move instruction, moving one chunk of data, one word to another word. Here's a little video of it. I think we just did that. I'd rather see the real thing anyway. So, we have a mask move instruction. Data must pass through a mask. Now you're going to ask, well, why do I want to mask off some of my data? Well, you probably don't hardly anymore, but remember how I told you how like old barcode scanners or a thumbwheel switch work, and how we hooked to like 4 inputs and got a binary number? Well, if we had an input card and we used the first 4 inputs for like a thumbwheel switch, then we could mask that data off and we could use the rest of the input cards for actual push buttons or sensors. We can mask the data coming off something. So it's pretty easy to see that. I'm going to modify this instruction to a mask move. I think I'll go over here to binary. Let's do some binary data here. I'm going to put a mask in here, and let's say I'm moving the last 4 bits, and that's all I want. So I'm going to put a 1 tab, 1 tab, 1 tab, 1 tab. Okay, notice my mask move is active. Now here's how it works. There's a source, which is B3:0. There's a mask, which is B3:1, and a destination, which is B3:2. My mask, the first 4 bits have a 1 in them, right? You imagine it like a gate. I'm going to let any data up here fall through down to this point. The rest of it doesn't. Now watch. I'm going to put some stuff in there. Notice it doesn't get through, right? Nothing come down here. I put a 1 up here, I'm moving data from here to here, but nothing got through. However, I've got a mask on the last 4 bits. That data got through. It's a gate. It's a gate for bits, basically. Does that make sense? All right, let's look at the PowerPoint. It's got some examples. Okay, here's another example. Here's our source right here. And here's our mask. It looks like we're letting everything through here except these 4 bits. Okay? And so if we look up here, this got to fall through. I'm sorry, you got to look. Yeah, right here's the destination. This got to fall through here, this went through, etc. Everything went through except for the mask. was at, and it did not change. There's a BTD instruction where we can move the bits through there. All right, I'm going to gloss over this because I just not really use that much. The one time I've had to use that was for, they had a barcode scanner that was 16-bit moving. They'd upgraded and they were moving to a 32-bit processor. Well, whenever you pulled the data in, it wouldn't segregate the data. It just put it all in one 32-bit word. So I ended up with two numbers in one slot. So I had to go in there and take the last 16 bits of that number and yank it out and move it around manually. So I got the correct barcode into the new 32-bit PLC. And I had to use a BTD instruction to pull that off. Basically, it stuck the wrong data in a 32-bit word, and I had to pull the last 16 bits off and move them around manually so I got the correct barcode in there. We can use them to change the preset of a timer depending on a speed selection. So maybe you have a switch that says, when I'm running product A, I need a 5-second delay. When I'm running product 10, I need a 10-second delay. So we can move them into the destination of a timer. Here they're moving it. See the little switch? So they can move different presets in there depending on what they want to do with it. Okay? Here they're moving a different preset. Notice the preset changes in the timer depending on the position of this switch. Do the same thing with the counter. Notice the destination is C5:1.PRE for preset. You can even move into the accumulated value. You know, I told you how counters need reset. Stick a 0 in there. You can't do that. Depending on your circumstance and what you're doing, you might do that too. I don't know. This does the same thing. They just moved it in here, and now they're moving the data from N7:1. When you see when you see the N7 data type or the N data type, that's a signed integer, right? Which has a value of, get close. Come on, somebody speak up. What's the max range of it?
37,000.
All right, 2.
67.
No. Signed integer is positive and negative, so it's about negative 32,768 to positive 32,767. Thereabouts. If you want to know what that range is, I tell you just type a big number in an integer file and it pops up and tells you, hey, here's your range, and you can't do anything else. Because I always get it mixed up and forget. But if you want to know what your range is on a number in the software, just come over here to an integer file and type a big number in there. There. Tells you what it is.
Why is the negative number 68 and the positive number 67? Digits.
Well, because it's one off. You got to take you got a 0 in there, so that makes sense. Yeah, you got a 0. Zero's a number too, so it shifts at 1. Since we're doing this with this new software, let's hit the pause button. Okay. So we can move chunks of data. Whole chunks of data. Whole files of data from one file to another. Here we have We can move those chunks of data within a word or from one word to another. All right. So you're going to ask, well, why do I want to move a chunk of data? Maybe you got a big recipe. Maybe all of these words contain set points for the oven, product flow for the brine, whatever you're running. Maybe you got a big roaster and you want to move different set points. Maybe you need X number of ounces per minute of salt or oil or whatever, right? So you then move that product data over and you run it. Palletizers, every time you stack a different size box. I don't know if some of you seen palletizers or not, but basically they come down through there and they've got little bumpers and shufflers, and they shuffle different size boxes around. They're programmed to stack them up, because you can't just stack boxes on top of one another, put them in a pallet and expect them to stay there. That's why you don't really see square boxes. You know why you don't see square boxes, shipping boxes? Because if they're going on a pallet, they can't cross stack them. So they want them rectangle, because it makes the pallet more stable for shipping. You can't just stack up square boxes because they're going to sit there and rock around. You want something that's rectangle so you can mix and match. Typically it'll be, you know,
I always thought they did that to tie it in.
well, they like a Jenga block. They stack them like Jenga blocks so they don't fall over during shipping. So, let's look at there is also a foul. This will actually do copy data, and it does math on it while it does it. I would show you that, but our processor's a little old and it doesn't support it. I've never seen one in my life. I think I had to use one time. But there's another way. You can just move the data and then do a different math instruction. You don't have to do it all at once. But if you could, like you want to multiply N7:0 by N7:1 and put the result in N7:3, you could do that, and you could use this right here to do all of the first words of 100 files and do all of that. Does that make sense? You could do it 100 times with this. Instead of putting 100 math instructions, you could do it all in one instruction. So what are they talking about? File, math, file. See, you got the place for the expression. If I was to put a math expression in there, they would do some multiplication or division or whatever. But, so, let's go over here because, here we go. Copy. It's typically what you're going to see. It's copy instruction. Pretty simple. We're going to copy one chunk of data to another place. So let's do that. I'm going to go offline. I want to make another data table. Go offline. I'm going to right click on my data file, select new. I want another integer file. And let's put 10 in there. Alright. Notice I have another integer file. We can call it integer if we want to. There it is. I got a chunk of data here and a chunk of data there. So I'm going to download it. So it's in the processor. Alright, so we're going to get rid of this. Come over here to move. It's file miscellaneous. We're going to put in a copy. Now, let's do, we're just going to copy N7:0. And we're going to copy it to N7:9. Okay. Right now that's being told to copy every time, and so it's taking N7:0, put it right here, taking this data and moving here. See, if I change that data here, it gets moved over. It's moving it a length of 1. That accomplishes the same thing as a move statement we looked at earlier, but it's got a length of 1. If I would like to move more data, I give it a higher length. Because it doesn't count words, it counts the starting address over. So it's going to do the starting address with 1. If I would like to move 2 words, if I want to move 2 words, I would change my length to 2. And so let's do 1 word. We're going to move 1 word. Now we're going to move the second word. Notice right here, it's done the next one. You with me? It's all it does is you tell it the length. Now, I don't have to move to a different destination. I could move data within this data file. So maybe I want to move these 2 to the last 2, right? See that? I'm going to take 1 and 2 and I'm going to move them right here. So I'm going to come over here and I want to start at N7:8. So my destination is going to be N7:8 now. And it moves 1 and 2. So now we're just moving data from here to here. Now, I'm going to show you how you got to be careful about that. I think what I want to do is I'm going to try to move this data here, only I'm going to make a mistake, and I'm going to try to move the data here, here, and to a place that does not exist. So I'm going to change my length to 3 and accept the rung edits. Oh, well, I couldn't trick it. Sometimes you can, depending on the firmware, let's see if we can do it here. I think maybe, let's try to go to N7:9. See if I can catch it. Yeah. I've seen it where you, depending on the firmware version, that you try to move it someplace it doesn't exist, it'll fault the processor. Okay? So, that didn't work. I was trying to fault the processor. It gave me an error, but I have seen it where it would let you try to do it and it would run out of room to put it, and it would fault it. So does everybody understand what we're doing there with our copying? We're just moving data around. So I skipped over some of these instructions just simply because you know, we're limited time here, and you know, probably not, I hardly ever see them. So let's look at this, a fill instruction. All right. Well, basically, you can fill data. Let's put this in here. We can clear out data. Where's it at? FLL. Okay. What a fill instruction does is it takes the value of one word, N7:0, and fills it to a specified length. So I'm going to fill up this word right here with one word's value. That makes sense. I'm taking the value. I'll show you. Let's just change the length to 10 here. So I'm doing the manipulation on the whole data table. And it's a way you can use it to clear out data if you need to blank data instead of having to do an individual move instruction. So I'm going to take the value of N7:0 and I'm just going to put 20 in there. And it moves it starting here, N7:9, right here, and it counts over 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it fills it up with the value of N7:0. So if I just put a 0 in there, I could blank everything out. That's all it does. You fill up a data table with one word. Everybody understand? Look me in the eye and tell me you understand the fill. We're just filling up the data files with one word. All right. Well, here's my data file. Here are my eggs. Do I want to tell the PLC to do this? Then I'll have to tell it to do this again. Or do I want to tell it to take that whole mess of eggs in one whack and just dump it in there? That's it. One whack. It's easy. I could tell it to do it 12 times, or I could tell it to do one time and simply, I know that every slot is going to have the same data, egg, and I just fill it all, throw all the eggs in there.
You want the same information in every slot.
In every slot. Having technical difficulties with my screen right there. I wanted to shift for some reason. Data compare instructions. We can compare data and make a decision based on it. Anybody remember those symbols? Equal to, greater than or less than or equal to. So there are compare instructions. Then we can also check for a range. A limit, LIM. We can check for a limit instruction. We can test a range of numbers and see if it falls in the limit. What's my cooking temperature in my oven? Well, I need to make sure that it's between 100 and 110 degrees. So I'll put a limit instruction, and if it's not between 100 or 110, then I'm going to turn on a buzzer, because we're making raw product. Probably be more like 250 degrees, but anyway. So there's all these instructions. I'm not going to go through all of them because they pretty much do what it says. So let's just start with a few of them and look at it. So I'm going to turn the light bulb on when data matches. Alright, so let's do a rung edit here. Let's get rid of this fill instruction. Let's come over here to compare equal to. Let's get a light bulb. Here's our light bulb. We'll just call it the true light. We're going to have to pick a source. So right here it's showing the current value of the data table is 0. So N7:0 has a 0 in it, and N7:1 has a 0, so that's true. Put a 1 in there, it becomes false. If I update the other data table word, now it becomes true again. It's an equal to statement. It's comparing these two numbers stored here. Now, I don't have to compare two data files. I could put a static number in there. See if it's right there. You only do it in one place, yeah. So, alright, so now I've just hard coded the 1 in there. Does that make sense? I've typed it in. So now it's not a variable, I can't change it, but if I put a 0 in there, it's not true. If I put a 10 in there, it's not true. It has to be a 1. Alright. So, let's change our instruction type. Kind of look at some of the different ones. We can go compare, we can do a greater than, GRT. I'm going to change my number to 5. So the value in N7:0 is 1. I'm testing it against 5. So look at this right here. Do you see this? See the logic symbol there? So we're testing if A is greater than B. So the value of A, here's source A is 1. Is it greater than source B, which is 5? So is 1 greater than 5? No. Change it. 5 is equal to, so that doesn't count. And once we become greater than 5, it becomes true. We turn on the light bulb. Now, I can do a greater than or equal to statement here also, which is GEQ is the instruction, GEQ. So if I do that, so now, if I put a value of 5, it's still true because it's greater than or equal to. Alright, now I can repeat that procedure with all the rest, but I'm not going to do that because we had greater than or equal to. Just remember the alligator eats the big number, right? Okay, so we've kind of gone through all of these. Here's not equal to instruction. As long as it's not equal to, it's true, it works backwards, right? See this not equal to instruction right here? It's comparing to 25, N7:5. So, what would make that light bulb go off?
Anything but 30? Right.
Anything but 25.
Oh, anything but 25.
It's the opposite of an equal statement. If an equal statement, it would have to be equal to 25. So basically, not equal to is anything that isn't equal to 25 would make that true. Everybody see it? It works backwards.
Be less than or greater than, either one will work.
Yeah. Greater than instruction. Here we're comparing the value of an accumulator with 200. You could actually do something else. You could have a timer start, and maybe the timer halfway through you want to do something, and then you also want to do something when the timer's done. So you could just compare the accumulated value. When it gets greater than halfway, you could do something, and then when it gets done, you could do something else. My personal suggestion on that is to put 2 timers in there, but that's easier for people to understand. You could do it. Like I said, there's a lot more stuff in here. You can do all kinds of things. Less than, greater than or equal to. I'm not going to go through all the... All right, here we go. Limit. Now, what did I tell you yesterday about your stoplight? How many people got all the way through and did both stoplights on your trainers?
I did one side.
Just did one side? How many timers did you use? 3? You did both sides? Probably you might use 6, or you could probably use some complicated and or normally closed, normally open logic, comparing the other lights to make sure they come on in the proper sequence. I want you to do it with 1 timer today. We're going to do it with 1 timer. Yep, I'm going to do it with 1 timer. We'll show you how. You're going to use the limit instruction. Alright. So let's look at our limit instruction. So I'm going to test the value of N7:0. Now I could have a low limit and a high limit. They could actually be integer files, so they'd be variable. You could change them. I'm just going to test a range. I'm going to test 1 to 10. So, here's our low limit and here's our high limit, right? Low limit is 1, high limit is 10. We're testing the value of N7:0. When it falls between this range, it becomes true. And these are basically, you could do the same thing with a compare instruction, or you could use 1 limit instruction. So what we're doing is we're comparing, is it greater than or equal to 1, but less than or equal to 10? Is what we're comparing. Because if I come in here and I put a 1 in there, it's still true, right? Still true. If I put a 10 in there, it's still true. If it gets outside that range and I put 11 in there, it is no longer true. If I get a number lower than 1, like 0, it's no longer true. Now, so we're testing a range between 1 and 10. Now, we can flip it. We can test outside that range. Now we're becoming true when it's inside that range. If I want to test it outside that range, and I'm going to have to repeat this because on the limit instruction, if the low limit is higher than the high limit, the instruction works backwards. We test outside of a range. If the low limit is higher than the high limit, then we're going to work backwards and test outside that range.
So you just
If the low limit is lower than the high limit, we're going to test inside that range. I'm sorry?
So you just flip it then basically?
Yeah. We're going to make the low limit 10 and the high limit 1. And so now, any number that is outside the range of 1 to 10 is true. If I was to put a 1 in here, come on. There, we're testing inside that limit. You always got to remember, on a limit instruction, the number here is still going to count true if it's equal to that number. So it's still always going to be equal to the high limit or the low limit. If I go to 9, it's still false. If I go to 10, it becomes true again. That's how limit instruction works. So what you're going to do today is reprogram your stoplight to work off limit instructions to turn your lights on instead of doing all those timers. We're going to do a one timer. I'm going to show you how to do a recirculating timer. Let's see what else is in here. I think we're about through with all this, to tell you the truth. So we've looked through all the limit instructions. There is a mask equal to instruction. What it's basically looking for on a mask equal instruction is, let's say we've got some kind of limit switches and you've got some machine, and in order to run product A, all this stuff has to be set in the correct position. Are you with me? Limit switch 1 has to be on, and then limit switch 2 has to be slid over and it has to be off. Some configuration that makes it run this product. So I've selected product A, and in order for me to let the operator turn on the machine, I have to make sure he set it up correctly and moved everything where it's supposed to be. So if I put all those limit switches on one card, I could say that when the data at the source location matches the data at the compare location minus the mask, because maybe I only got 8 limit switches and the rest of the card is doing something else, so I don't use those last 8. Then I'll let it come true. That tells me he's got the machine set up. I could program some conditions just using normally open and normally closed, which would probably be a better idea because a lot of people don't understand that. So it'd probably be a better idea to program some conditions to say that if you want to start when product A is active, then this limit switch has to be off, this limit switch has to be on, do normally open, normally closed, and then turn on a bit. And say that that's the condition. That would probably be an easier thing to do, to say that all this stuff has to be shifted this way in order to run, than to do this instruction. Personally, I've never used it. If I was going to do something like that, I would use normally open, normally closed instructions in a certain sequence to turn on a bit saying that you've got it set up for product A and it's okay to run. That makes sense? Here's some data manipulation programs. Here we're comparing the accumulated value. I told you we could do things. So if the solenoid A is on, we start a timer for 15 seconds. When it gets to 5 seconds, we fire solenoid B. When it gets to 10 seconds, we fire solenoid C. And then once the timer is done, we fire solenoid D. Does everybody see that? You could have done it with cascading timers also.
That's how you're going to set up a stoplight, huh?
Yeah, but we're going to use a limit instruction, so we don't want to do 2 instructions. I'm going to show you how to do a limit instruction. Here's some equal to instructions. It just says if the accumulated value is equal to 5, we're going to latch on a light. When it's equal to 15, we're going to unlatch the light. So That light will be on when that timer is between 5 and 15 seconds. The light will be on. Everybody see that? See, this timer has got a 20-second. So when it's equal to 5, it comes on, and when it's equal to 15, it goes off. So the light will be on between 5 and 15 seconds, which will be a total time of what?
20.
10 seconds.
Oh, okay, I'm sorry.
That was a trick question. I see. Good job, David. Here's some less than statements. We can compare counters also. You can compare whatever you want to. Here's a vessel filling operation. It says the receiving vessel has its weight monitored by the PLC. When the weight reaches a preset value, the flow is cut off. Should the system leak additional material into the vessel, the total weight of the material could rise above the preset value, causing an equal instruction, if used, to go false and the vessel to overfill. Here is a BCD. You don't ever use those. We don't use thumbwheel switches anymore. So remember we talked about that. Watch the video on BCD instructions. Here's a BCD input module with these thumbwheel switches. Now we have touchscreen. We can hook up, basically, you're just converting, you can monitor the setting of a thumbwheel switch. We don't ever use thumbwheel switches. Analog modules, you know how those work. Let's see what else. You can use them to monitor the value of an analog module, just like I told you about monitoring the temperature of an oven. We have a closed loop control. Here we have a controller. We're monitoring a value. We get a feedback system. So what about like an on-off system? What if this is monitor the temperature of a tank of water with a limit instruction. When it becomes over temp, I open up a valve and dump cold water in there until it falls below temp to the right range, and I shut the water off. And I'm filling it with hot water. So the water cools off, I fill it with hot water until it reaches its limit, and then I turn it off, and I repeat. On-off proportional control. That makes sense? And I can do that with limit, greater than or equal to instructions, whatever you want to do. Here we have just what I told you. We have a thermocouple. Basically, it's a heater right here. And so this would be, a limit instruction would accomplish the same thing as these two instructions, basically. But basically we're saying if it's less than here, then we're going to turn it on. If it's greater than, we're going to turn it off. We have PID proportional controls. I have a nice little video on PID control, but basically, they don't go into PIDs here. We got another video for that. Before we take a break, I want to show you about a recirculating timer, because I told you on your exercise you were going to use one timer, right? You'll see these quite a bit. It's just a timer that just keeps a count and spins around and around. And it's just a little bit of logic. It's real easy to do. If I want to make a recirculating timer, I'm not going to have anything that turns it on besides the timer. Let's do TON. Maybe we'll do 10 seconds. So the logic on here is when the timer is not done, it's true. So at times when it gets done, guess what? That changes really fast and it resets. So as long as it's not done, it's active. When it becomes done, it resets. Because we break the logic to the left of it, it's going to reset, right? And what we've done is we just make a recirculating timer. I could do it that way, or I could do it another way, but that's the easy way. You just do it in one run. I could do it this way, accomplish the same task.
You said we gotta have all 3 lights hooked up to it though too, right?
All 6.
All 6,
It's easy.
I guess.
If you know what you're doing.
I also have an example.
So they're all gonna be the same timer? Is that what
Just
you're
use
saying?
one timer.
I got you.
I could also do that.
But then you do the same, you start
It-
your
It
next-
accomplishes the same thing. You don't see anything happen because it's really fast. It doesn't have time to update the computer. That's why you don't see the done bit turn green, because it happens too fast for the computer to update it. So that's a recirculating timer, and I believe that takes us to break time.
Yes.